Welcome to another video by Dr. Viv. This time we'll dive into the concept of conservative forces, associated potential functions, and situations in which either of these things is not true. And that's closely related to the failure of a famous theorem in mathematics known as Stokes' theorem. So the example I have here is the work done by a vector field. A vector field is a assignment to the space of a vector at every point. So you can see that this function f of x, y, z, first of all, does not depend on z. And secondly, it does not have the z component. So those are two separate things. The fact that it doesn't depend on z means you don't see z here or you don't see z there. And the fact that it doesn't have a z component means that the third term, which will be plus some function of x, y, and z k hat, is missing. So it's just a two-dimensional function of two variables, in other words. And we have to find the work done along the indicated path here. The path goes from -1 to 1, and then from 1 to positive 1 on the y-axis to positive 1 on the x-axis. Now, if you didn't know anything about anything, you can still do this problem by using the definition of work done. And that's going to be my approach in the initial part of this video. I'm going to pretend I don't know anything about conservative fields or potential functions or Stokes' theorem, and I just want to do a honest integral. Well, there's always room for honest work in this world. So let's proceed by that principle. So the work done by a force, let's recall. Along a path, gamma is W gamma would be the integral of f dot dr along that path gamma. So that's the basic definition of work done by a force. For example, if I have a path gamma, some initial point I, and some final point f, and then along the path gamma, there is this dr vector, and the force can be acting in any direction, some direction like that. You take the dot product, which involves, of course, the angle between f and dr, and that angle can keep changing from point to point. For example, the force could be like that, it could be here, and the drs also keep changing. And this is a simple path. I could have made the path much more horrible. So in general, it's a pretty awful integral to calculate. This is called a path integral. But that's the world of physics. Physics is full of paths along which we have to evaluate the work done. So this can be done. All we have to do is set up the integral and calculate it for each of these paths. So just for simplicity, let me call this path gamma 1, and I'll call this path gamma 2. That way we can separate out the work done by the force along gamma 1 and the work done by the force along gamma 2. So first of all, we have to find an equation for these paths. Now, I like to use the traditional way to find equations. Now, I don't know, I've talked to students over the years, and apparently it's not very popular. But where I did my schooling, which is in India, this is a popular way of thinking about the equation of a straight line. This is sometimes in textbooks, if you want to put a name to it, it's sometimes called the intercept form of a straight line. Well, anyway, what is it? You have the x-intercept, which is a, and the y-intercept, which is b. And the intercept form says that x over a plus y over b is equal to 1. You can immediately test that it is true. For example, when y is 0, which is this one, what do you expect? You expect x to be equal to a. Let's see if that equation proves us right. When y equals 0, I have x over a equals 1, and that gives me x equals a. So that makes sense. Let's try when x equals 0. When x equals 0, I must have y equals b, because x equals 0 is the y-axis. So let's put x equal to 0 in that equation. I get y over b equals 1, and that indeed tells us that y equals b. So this works. The intercept form is by far my most favorite straight line. So the path gamma 1, if you look at the path gamma 1, I can write it as follows. It's x over negative 1 plus y over positive 1 equals 1. And said another way, it is y equals, that's a negative x. So bring it over the other side. So I get y equals 1 plus x. So that's our path gamma 1. While we are at it, let's also find the equation for path gamma 2. That's x over 1 plus y over 1 equals 1. And that's what you expect, x plus y equals 1, which tells me that y equals 1 minus x. You can immediately see my goal here is to eliminate the variable y. If you eliminate the variable y, the integrals just become one-dimensional. It's just x all along, so it's pretty easy to do. Well, easy in the sense it's doable. Okay, so let's write down the integral definition of the work done. The work done along gamma 1. F dot dr simplifies to fx dx plus fy dy, because that dr thing is just dx I hat plus dy j hat plus dz k hat. In this case, we don't have the k hat component, so fz does not exist, so that does not contribute to the work done. Now, along the path gamma 1, we also have that what do we have? Dy can be eliminated, like I said. So if I differentiate both sides, I'm going to get dy equals dx. So that's really nice. It looks like my integral along the path gamma 1 can be calculated rather nicely. So I'll keep that here and move on to the calculation of that integral. These integrals are actually easy to do, so I will do them. But if they're complicated, you know what to do. Just go to computer software and put your answer in there and see what you get. Because the integrals are rather elementary, I will do them for you. Now let's write down the expression f sub x dx, f sub y dy. That is f sub x and that is f sub y. So let's write them down. So I get w gamma 1 equals the integral f sub x dx plus f sub y dy along the path gamma 1. I repeated that earlier step. And then for f sub x, I'm going to write negative y over x squared plus y squared dx. And for f sub y, I'm going to write positive, that's f sub y, so that's positive x over x squared plus y squared times dy. So we basically have our work cut out for us. All we have to do is substitute y equals 1 plus x into everything and make it an integral purely in the x domain. So that gives me the integral from -1 to 0, because remember the path, since I'm only worried about the x, it goes from -1 to 0. And for y, I'm going to write 1 plus x dx over x squared plus 1 plus x squared. And then here I have x divided by x squared plus 1 plus x squared. And recall that dy was equal to dx along path gamma 1. So I'm going to write this as dx. So that's a integral purely in x variable. So now we'll continue to work on it. What I would have to do is realize that I have a negative x here and a positive x here, so they cancel out. So I'm just going to get negative, the integral from -1 to 0. So I'm going to get, I'll take the negative sign outside, dx divided by x squared, and expanding the denominator, I'm going to get 1 plus x squared plus 2x. So let me simplify the denominator some more. It's the integral from -1 to 0 dx over 2x squared plus 2x plus 1. And now I have to complete the square, which is the usual procedure followed in calculus with these kind of functions known as rational functions. So 2 times x squared plus x. Now to complete the square, I'm going to add and subtract 1/4. Okay, and then I'm just left with that plus 1. Okay, now we are in a position to complete the square and then make a u substitution. So that's going to be our next step. So one more step before that, negative integral -1 to 0 dx over 2 times, this is x plus half squared, and then I have 2 times -1/4, which is -half. -half plus 1 is +half. So all that I've done. Now for the u substitution. Now, from experience, I know that the u substitution I need to make for this particular case is going to be something like this. So I'll just make it and we'll see it works. It's 2 times x plus half should be equal to u. Well, if that is the case, then 4 times x plus half squared is equal to u squared. But I don't have 4, I have 2 here. So 2 times x plus half squared will be u squared over 2. Now dx, 2 times dx, if I differentiate this main equation, I get 2 times dx equals du, which means that dx is du divided by 2. Now limits. You've got to go through all these steps when you change variables. What are the limits going to be? Well, first of all, when the lower limit first, when x equals -1, what happens to u? U is going to be 2 times -1 plus half. That's going to be 2 times -half, which is the same as -1. Now, what about the upper limit? When x equals 0, u will be equal to 2 times 0 plus half. 2 times half is 1. So that's plus 1. I just like to be careful with all these steps because if you make a mistake, you have to go back and change all the work, and it's just not worth the trouble to do that. So I like to be careful and eliminate that silly errors like that. So once we have all this, let's find out the work done. W gamma 1, we're back to W gamma 1. Is going to be negative, the integral from -1 to 1 dx, which is du over 2, divided by u squared over 2 plus 1/2. So you can see that there's a 1/2 in the numerator and a 1/2 in the denominator, so we can immediately cancel those. And I get -1 to 1 du by u squared plus 1. Well, that anybody can tell me what it is. It's the inverse arctangent. So that's negative tan inverse of u between the limits of -1 and +1. So that's minus tan inverse of 1 minus tan inverse of -1. Now tan inverse is a odd function because tan is an odd function, and tan is an odd function because tan is sine over cosine, and sine is odd and cosine is even. So the ratio of an odd function and an even function is once again odd. So upshot is that minus can be made into a plus, and I get just 2 times tan inverse 1. So I get -2 times tan inverse 1. Well, tan inverse 1 is pi over 4, so that's going to be 2 times pi over 4, which is negative pi over 2. So I found the work done along path gamma 1. Now, for the next calculation, the work done along path gamma 2, the only difference is that the path changes. Okay, so I now have y equals, for gamma 2, y equals 1 minus x, and dy is now equal to negative dx instead of positive dx. That's about the only difference. And well, the limit also changes. X goes from 0 to +1. All right. So the work done along the path gamma 2 can be written next. Integral from 0 to 1. Now keep in mind that's negative y dx over x squared plus y squared plus that times dy. Well, but dy is negative dx over x squared plus 1 minus x, the whole squared. So once again, let's simplify this. When we simplify this, we'll notice that there's a positive x dx there and a negative x dx here. So those will cancel out, and I again end up with just the constant term in the numerator, just like last time. So I get integral dx over, and now I'll expand the denominator. I'm going to get x squared plus 1 plus x squared minus 2x. And then I have to complete the square once again. So it's just rinse and repeat, except the denominator is slightly different. So it's going to be negative integral 0 to 1 dx. Now I'm going to complete this. I've completed the square I have to do next. So that's going to be 2x squared minus 2x plus 1. Integral 0 to 1 dx. Take 2 outside, then complete the square. So that's x squared minus x plus quarter minus quarter plus 1. So you don't mess with that. you just try to complete the square with just the first two terms with the coefficient of the x squared taken out. That's what you learned in high school. So this gives me negative integral 0 to 1 dx over 2 times x minus half this time squared. And then I have 2 times minus quarter, which is negative half, plus 1, which is again positive half. Same U substitution can be used. Technically, I should call this W substitution or something because I've already used the symbol U once, but we are in grad school. We know what's what. So let U equals 2 times x minus half. So just like before, 4 times x minus half squared equals U squared. And that means that 2 times x minus half squared is U squared over 2. The limits are, we'll check the limits next. X equals 0. What happens then? When I put x equals 0 here, I'm going to get U equals 2 times negative half, which is minus 1. And when x equals 1, I get 1 minus half, so U becomes plus 1, just like before. So our answers will also turn out very similar. Let's look at what happens. Let me just save this sheet over here to see what's happening. So W gamma 2 next is negative integral 0 to 1 dx, which is one more step. What is dx? Well, du is 2 dx. So this tells me that dx is du over 2, just like in the previous case. Okay, so let's put all this together. Dx is du over 2. And then I have U squared over 2 plus half. Exactly the same procedure, cancel the halves, and the integral of du over 1 plus U squared is tan inverse U. So I get minus tan inverse, sorry, the limits are U equals minus 1 to plus 1 here. Tan inverse U between negative 1 and plus 1. So it's identical to what we did here. There's just no difference between that step and this step. So I'll just write the answer immediately. It's negative pi over 2. Beautiful. The total work done, because work is a scalar, is additive. So W gamma, W net, I'll call it W net, is W gamma 1 plus W gamma 2. And each one is negative pi over 2. Negative pi. The beauty, the deceptive simplicity of this answer should convince you there's something very fundamental and very deep that's happening in this problem, which we have not scratched. And we are far from understanding what it is. If we continue in this rather dumb fashion for every problem, we'll never find out the deep things that are going on under the surface. So now we'll raise the level a little bit. We're now going to talk about the notion of conservative. Okay. Conservative force. Conservative does not have anything to do with politics. Conservative force is said to be conservative if one of many things holds. I'll keep rattling them off as we go, but the most basic requirement for conservative force is that the curl of F must be equal to 0. And if the curl of F is 0, then the force is said to be conservative. Let's check if the curl of F is 0 in this case. This problem is really interesting and really deep, precisely because the curl being 0 is not enough to decide if the force is conservative. So that's the beauty about this problem. It's used as a counterexample in many math textbooks for that reason. Let's calculate the curl. The curl is given by, now don't forget that the nabla symbol, the gradient, is I hat del by del x plus j hat del by del y plus k hat del by del z, which I sometimes like to abbreviate as I del x plus j del y plus k hat del z. So when you calculate the curl, the first step is to write I hat, j hat, k hat, and then I have del x, the components of the curl are next, del x, the gradient operator are next, del y, del z, and then lastly, the components of the force function, fx, fy, and fz. Well, we already know that we don't have fz in this problem, so let's write this down. That's I hat, j hat, k hat, del x, del y, del z, and fx is this one. So that's negative y over x squared plus y squared. And then fy is x over x squared plus y squared. And fz is 0. Now, when you try to find the I hat component, you'll find that you have del y times 0, which is del y of 0, which is 0. Del z of x squared plus y squared, that's 0 too, because there's no z here. What about the j hat component? When I do the j hat component, I have to block out this and I have to block out that. So I'm going to get del x of 0, that's 0. Del z of that, that's again 0. So it looks like only the k hat component survives. I'll soon plot this vector field to show you why it's the k hat component that survives. And the k hat component is k hat times del x. Let's use flower bracket now. Del x, x over x squared plus y squared minus del y of minus y over x squared plus y squared. So that's the curl. Let's continue to evaluate the curl next. So I'll move this over here. Remember the quotient rule. The quotient rule says that when you take the derivative of a ratio of functions, you have to get the low times the derivative of the high minus high times derivative of the low, what you learned in basic calculus. So let's do that. This is going to be k hat times low d high, the derivative of x, because this is del x, remember. Del x is 1 minus high d of the low function, but the d is with respect to x. So when it only sees x squared, it doesn't see y squared. So you're going to get 2x. The partial derivative is that divided by x squared plus y squared whole squared, because the denominator gets squared. And then this minus and that minus interact, producing a plus. So I'll just call that plus. So imagine that you don't have a minus anymore. And then again, low d with respect to y of the high, which is 1, minus the high, which is just y, times dy with respect to the low. Well, that sees only y squared. So I get 2y over denominator squared. So a faithful application of the quotient rule is what I've done there. Now, this should be 0. That's x squared minus x squared. So that gives me y squared minus x squared there. And here I'm going to get x squared minus y squared. This is 0. The curl of this force is 0. So by the conservative forces, when the force is 0, you can actually show that the work done is path independent. So let's go ahead. If the work done is path independent, there's a much cooler way to find the work done along path gamma 1 and then gamma 2. So if we had known this beforehand, so I just wanted to make a comment which is very important, and that is there's something weird that happens to this function at the origin. Well, the weird thing is it blows up. So let's try to plot this vector field. You can, of course, plot it on Desmos or Mathematica or Maple, but I would like to plot it in a simple-minded fashion. I'm going to plot it around a unit circle first, because around the unit circle, the denominator is just 1, because the equation of a circle is x squared plus y squared equals 1. So if I constrain myself to the unit circle, the vector field becomes really easy. The vector field constrained to the circle is just going to be negative y comma x. That is, the x component is negative y and the y component is positive x. So let's plot it in a few places. If I look at, let's say here, when y equals 0, it's going to be 0, x component is going to be 0, and the y component is going to be 1. Sorry, that's our vector field there. Next, let's try to plot it over here. When x equals 0, that's when it comes over there. When x is 0, I get negative y. So that it just goes around like this. So we already know, based on basic thinking, that this is how it goes. So that's a curl. And you notice that it comes back to the original position and it keeps going around like this. So this is interesting, because as you come closer and closer to the origin, what happens is the numerator and denominator is still negative y and x, but that's still negative y and x, but the denominator keeps going bigger and bigger. So it's going to blow up here. That's a singularity. It's like a black hole. Because of that singularity, something really interesting happens when you go around a complete path. When you go around any path that includes a singularity, the conservative force theorems fail, and Stokes' theorem also fails. We'll look at that later. But keep that in mind, keep that figure in mind, and let's move on to the much cooler way to solve our original problem. Now, the way I did it was tough. It took me nearly half an hour to finish the calculation. Now, this much cooler way will probably take us only a few minutes. And the conservative forces theorem says that if the forces don't blow up and along any path you choose, if the path is closed, the work done is 0. So let's just make that statement. If the function f is smooth in a domain, then the work done along the boundary of the domain is 0. Smooth in domain and conservative is conservative. That's the first thing. And is smooth in the domain, then the work done along the boundary of the domain is 0. So the way we're going to solve this problem, the much cooler way, as I said, is going to be the following. I'm going to, instead of taking that original path, I'm going to think of a new problem. And that is this. Okay, I'll go like this, I'll go like this, I'll go back like this, and I'll go back like this. When I do that, the domain is the shaded area. Now, in the shaded area, nothing funny happens. I've told you the only singularity is at the origin. We are well away from the origin, so there's nothing funny happening. the function is completely smooth, it's conservative. We just showed that by computing the curl, and the curl is 0. So then this must be true. Now, why is this true? The proof comes from the Stokes theorem. The proof is the following. The theorem of Stokes says that under these very conditions, the following theorem is always true. Let's call the domain D, and the boundary of the domain I'll call del D. So this is the domain, and this is the domain boundary. And just for our future reference, let's call this green path with that arrow the path gamma 3. So I have all the setup for the theorem of Stokes. The theorem of Stokes says that with those assumptions, the integral, the closed integral along the boundary of the domain of f dot dr is equal to the double integral over the domain of the curl of f dotted with the unit vector, outward pointing unit vector to the domain times the area dA. So the outward pointing unit vector is got by the convention of the right-hand rule. If I go along the domain boundary with my finger to the right hand, the n hat vector is pointing up. So that's n hat, okay? And dA is just the area that I've shaded with green, with the green shading. So that's Stokes' theorem. Well, if f is conservative, the right-hand side is 0. If the right-hand side is 0, the left-hand side must be 0. And the left-hand side is just the work done along the boundary of the domain. So trivial proof. The proof is just immediate. Theorem of Stokes. Beautiful. So we're going to use that's proved. We actually proved it just by talking QED. So now let's apply the theorem of Stokes, or this theorem here, to solve our problem in a much easier fashion. Now, all this talking and setting up is taking time, but if once you know the ropes, this calculation is really short. So by the conservative theorem, I have the work done along the boundary del D is going to be 0, but that work is comprised of 3 parts. It's the work of gamma 1 plus the work of gamma 2 plus the work of gamma 3. Now remember, gamma 1 and gamma 2 is what we need. Therefore, the work done by gamma 1 plus the work done by gamma 2 must be equal to negative the work done by gamma 3. The work done by gamma 3 is very simple to find. And the reason for that is because the denominator is going to be simple. Along the boundary, along the domain boundary, we have the unit circle, or the upper half of the unit circle, and the function takes that very simple form. It's negative y comma x. So things get really simple because of that. So now let's work in polar coordinates. That makes more sense because you have a circular shape. So the work done by gamma 3 is our objective, because once I find the work done by gamma 3, the work done by the original problem is immediate. It's just negative of whatever I find. So this is going to be the integral. I'll just write this out fully. It's negative y over x squared plus y squared dx plus x over x squared plus y squared dy. Now is where I'm going to use the polar coordinate transformation, and that is x equals r cosine theta, but r is 1 since it's a unit circle. So x is just going to be cosine theta, and y is just going to be sine theta. Differentiate both sides, I get dx equals negative sine theta d theta, and this gives me dy equals cosine theta d theta. Now the path gamma, it goes from +1 here to -1 there, but if you're working in the polar coordinates, it just goes from theta equals 0 to theta equals pi. So now we can write our new integral as going from theta equals 0 to pi. Let's do that. W gamma 3 equals the integral from 0 to pi, negative sine theta dx is negative sine theta d theta X squared plus Y squared is cosine squared plus sine squared, so that's just 1. And then you have X, which is cosine theta, times dy, which is cosine theta d theta, divided by 1 again. So it looks like our problem is simplifying drastically, because that's just sine squared, because two negative signs cancel out. Sine squared plus cosine squared is 1. So I just have integral 0 to 1 pi of d theta. Well, that's the simplest integral in the world. It's just theta between 0 and pi. And so the answer is pi, which means the answer to our original problem is negative pi. That result, which we found with such great difficulty, can be got in 2 lines if you eliminate all the chatter I had in between. So that's a beautiful way of, that's a cool and a clever way of solving this problem once you realize that you have a conservative force. Now, there's a caution, and I mentioned this earlier. The origin is a dangerous point. You have to stay well away from it. If you don't stay near it, then using the same, suppose you go around the unit circle, and suppose you go around the unit circle many times, okay? So if you go around the unit circle, so let's think of a new path, capital gamma. You go around the unit circle n times. Well, this integral is not going to know about it. It's going to go around from 0 to 2 pi, and then 0 to 2 pi second time, third time. And so the answer we're going to get for the work done by the path gamma is going to be, each time you go, it get 2 pi. So it's going to be 2 pi n. This is a very important concept in topology. It's called the winding number. When you have a situation where you have a singularity and you go around, you get a winding number. It's a topological invariant for the circle. So the very complicated deep waters, and the mathematics is extremely sophisticated and beautiful. It's a little bit beyond the scope of even this graduate class, but I just want to tell you that if you include the singularity, there's a cost each time you go around. It's as though you're going around a lake. In the middle of the lake, there's some kind of monster, and each time you go around, something happens, and your clock gets reset, but your memory does not. So it's like Groundhog Day. So if you go around second time, your clock reads the time that you had when you started the first time, but you clearly have a memory of what you saw, like different kinds of birds in the first trip. That memory is not gone. So that's the kind of singularity we're talking about here. It's pretty awesome things. Now, the last concept is that of potential functions. As long as you stay away from the singularity, you can actually define a potential function. It's already defined for us here. It is theta. The potential function for this problem is precisely theta. And so we'll talk about that here. Item 2. If the force is conservative, then there exists that backward E is, there exists a potential function U, such that F is the negative gradient of U, or the work done by the force along any path gamma is going to be U final minus U initial. So this, the work done being the, it's actually negative change in potential energy. I always have to remind myself, so the work done by gravity, if you go from a lower location to a higher location, the work done by gravity is negative, and that increases the potential energy. So this has to be negative. Work done by gamma is UF minus UI. So you can do this problem like that also. Okay, you can find the final potential energy and the initial potential energy and wrap it up like that. So let's do this problem. The last step in this problem is to do it in that fashion. So that's yet another approach. So here I know the potential energy function, which I'll find out shortly for us. And then we can solve this problem by looking at the potential energy also. That's our path gamma 1, and that's our path gamma 2. The potential energy function, in our case, is going to be simply theta. So u r theta is just going to be theta, which is arctangent of y over x. Now, by the way, it's not a bad thing for us to verify that this is indeed the potential function, even though I get it from here. Let's verify it. Here's a verification. We have to show that that's true. So I have to show that fx is negative del by del x of tan inverse y over x. I'll just do fx, and I'll let you do fy as a homework exercise at home. So that's going to be negative. When I take the derivative of an arctangent, I get 1 over 1 plus y squared over x squared times the inner function. So the derivative of y over x squared with respect to x is just negative y over x squared. So the two negatives will cancel out. I believe I discovered a problem. The potential function has to have minus sign. Okay, that will take care of this minus sign, and so that will give it plus. Okay, now it's good. So this gives me the x squared will cancel out. So x squared plus y squared over x squared. So I'm just going to get negative y over x squared plus y squared. So that is the x component of our force function. Okay, so the potential function is negative theta. It's not a big deal. It's just that the definition of work done versus potential energy has this offset of negative sign. So we can actually find the change in the potential energy here, and the change in the potential energy there, and find the difference and show that the answer is negative pi. I think I'm going to do it just because it's a kind of a dicey thing to use this definition. So we'll find the change in potential energy, and then we'll make a minus sign because the work done and the change in potential energy are related by the minus sign. This is delta U. Delta always means final minus initial. So let's calculate delta U for this path and delta U for that path. So delta U total is going to be delta U1 plus delta U2. The potential energy change going from here to here, let me call this point I, let me call this point final 1 and this point final 2. Okay, just notations. So delta U1 is going to be U final 1 minus U initial. Well, this tan inverse y over x, if you just rashly put x equals 0, you're going to get infinity. So be careful. So that's going to be the limit as epsilon goes to 0 from the left of negative tan inverse y, but y is 1 minus x. So that's going to be 1 minus epsilon over epsilon. Okay, that's the final. The initial is going to be at x equals y equals 0, the x-axis. So that's just 0. So let's keep this in mind. When epsilon goes to 0 from the left, let's call this epsilon squared. When epsilon goes to 0 from the left, I have to put a negative epsilon squared to indicate that. Okay, so that two negative signs will cancel out. So I get limit epsilon goes to 0 from the left of tan inverse 1 minus epsilon squared over epsilon squared. So that's what delta U1 is. Let's just keep that result aside. Delta U2 is going to be U final 2 minus U final 1, but this time along path gamma 2. So for gamma 1, I'll just remind you that y equals 1 minus x. For gamma 2, I'm going to get y, this is y equals 1 plus x, I believe, sorry, plus x. And that's y equals 1 minus x. And so what I've done is I've put x equals negative epsilon squared is what I've done here. Here, epsilon comes to 0 from the right. So I only have to put x equals positive epsilon squared here. So I'm going to get limit as epsilon goes to 0 from the right, and negative tan inverse of y, which is 1 minus x. So it's again 1 minus epsilon squared over well, that's UF2 minus UF1, and I'm talking now about UF1, so I have to put a further negative sign there. UF2 is 0 because there's no y value there. So I just get this. I'm just getting this term. So that's why I have the negative sign there. That term is 0. Divided by x, which is epsilon squared. The two minuses cancel out, so I get limit epsilon goes to 0 plus of, again, the same thing, tan inverse 1 minus epsilon squared over epsilon squared. Well, the head rush moment is this last bit. So before making the video, I actually went to Wolfram alpha. So according to the gods of Wolfram alpha, the asymptotic expression for arctangent of zeta is the following. As zeta goes to infinity, it is pi over 2 minus 1 over zeta plus 1 over 3 zeta cubed minus 1 over 5 zeta to the 5, and so on. Okay, the denominator keeps increasing in odd powers. So as zeta goes to infinity, clearly all these terms go to 0, and I just get pi over 2. And so when I add these two, I'm just going to get pi over 2 and pi over 2. So the total potential energy delta U is just going to be pi over 2 plus pi over 2, which is equal to pi. And the work done along the gamma, which is gamma 1 union gamma 2, is just going to be negative delta U, which is negative pi. So in this manner, we have recovered the work done by using the potential energy concept also. So in this way, we see how, let's go back to the aims of this video. We wanted to see how the work done by a force ties into the concept of conservative forces, potential functions associated to them, and the possible failure of Stokes' theorem if the domain D includes